This animation shows a common misconception about AI. When you chat with a digital assistant, it feels like it knows you. In reality, large language models are stateless. An LLM, or large language model, is the underlying artificial intelligence engine that processes and generates text. By default, it retains no memory of past interactions. After every single prompt, its awareness is wiped entirely clean. This diagram represents the context window. To have a coherent conversation, you have to package your operating instructions, your factual data, and your conversation history into this strict, bounded workspace. It is the only place the AI can temporarily hold information to process your immediate request. Watch what happens as this window overflows. If you try to cram a massive, multi-day conversation into a single prompt, computing costs spike, and the model slows down. Even worse, the AI suffers from context rot. Context rot is a condition where a model loses its ability to pay attention to critical facts simply because there is too much surrounding noise in the prompt. Because the hardware strictly limits how much data the AI can look at once, we cannot rely on the model itself to remember everything. A truly personalized assistant requires a dedicated external data management system that dictates exactly what the AI sees and exactly when it sees it. Traditionally, developers relied on static prompt engineering, where they wrote a single, rigid set of instructions. Now, to build stateful, intelligent agents, we use a dynamic process called context engineering. Context engineering is the automated, turn-by-turn assembly of a state-aware payload tailored to the user's specific moment. Here we see a chef organizing their station, which perfectly illustrates the concept of mise en place. Before the cooking begins, the chef gathers the exact recipe, the specific knives, and the pre-measured ingredients. Context engineering does exactly this for an AI agent before executing a single line of reasoning. The system dynamically gathers several specific components. It pulls high-level system instructions that define the agent's persona. It fetches evidential, factual data to ground the reasoning. Finally, it retrieves the immediate conversation history so the model understands the current task. The goal is precision. By selecting, summarizing, and injecting only the most relevant pieces of information, the model gets everything it needs to perform complex tasks without hitting its computational limits. Context engineering relies on two foundational pillars, starting with the session. Think of the session as a messy, active workbench. It encapsulates the immediate turn-by-turn chronological history and the working memory of your current conversation. But as you keep chatting, that workbench fills up fast. To prevent the transcript from crashing the AI's context window, developers have to deploy active compaction strategies to shrink the payload. This animation illustrates two of the most basic approaches, sliding windows and token-based truncation. As the dialogue stack grows, the system simply slices through the timeline, keeping only the most recent messages and aggressively discarding the older half into the trash to stay under the token limit. Instead of deleting that history, a more advanced strategy called recursive summarization condenses it. An agent periodically runs a background process to condense the oldest messages into a dense summary paragraph, which is then placed right back at the top of the context window to preserve the narrative. Sessions are excellent for managing the immediate task at hand. However, because they are inherently temporary and specific to one interaction, building an agent that learns about you over time requires moving those insights into a permanent, structured format. That brings us to the second pillar, memory. If the session is the temporary workbench, the memory is the permanent filing cabinet. It persists framework-agnostic facts, preferences, and insights across multiple sessions, allowing the agent to continuously build an understanding of who you are. This flowchart maps out how memories are created using an automated ETL pipeline. ETL stands for Extract, Transform, Load, which is an automated sequence that pulls raw data from a source, cleans it up, and saves it to a database. Looking at the extraction phase, the system feeds the raw conversation log to an LLM. Rather than saving everything, this model is guided by strict topic definitions to filter out the noise and extract only meaningful, isolated facts about the user. Next is the consolidation phase. The system retrieves your existing memories and uses another LLM to compare them against the new facts. It automatically resolves conflicts, deduplicates information, and decides whether to merge, update, or delete records to ensure your profile stays accurate. This split screen shows how those consolidated memories are actually stored. On the left, vector databases store information as numerical arrays to help the agent find conceptually similar ideas. On the right, knowledge graphs store facts as a network of distinct entities and relationships, allowing the agent to reason about complex connections. By constantly running this automated pipeline in the background, the memory manager transforms messy, disjointed chat logs into a coherent, continuously evolving identity that the agent can reference at any time. This diagram illustrates the operational loop. The framework enters the hot path, fetching session history and querying the memory manager to prepare an optimized context payload. The model is then invoked. Finally, the system asynchronously uploads data, triggering background consolidation. This animated chart compares memory to RAG, a method for fetching static facts from external documents. While RAG makes an agent an expert on a specific domain, memory curates dynamic, personal behavior to make the agent an expert on you. Ultimately, a lifelong adaptive AI doesn't exist because of the model's inherent abilities. It is the result of context engineering, a meticulously designed system that seamlessly orchestrates the messy reality of the present with the curated knowledge of the past.